Welcome to section 7.2, partial derivatives. In 7.1, we studied change in a multivariable function by just changing one input variable at a time. The resulting changes were called partial derivatives. Before we get into the derivative formulas, so we can avoid that subtraction, let's take a quick look at what partial derivatives can mean on a graph. One way to visualize a three-dimensional graph on a flat piece of paper is with a contour diagram. And as I note here, these will not be on the exam, but they can be really useful for visualizing. We locate points with x and y coordinates. Then the curved lines are the contours and tell us how high or low the graph is above or below the paper. Contour lines can have negative number labels. So here to the right, we've got a contour diagram. The horizontal axis is our x-axis. The vertical axis is our y-axis. And we're going to estimate the coordinates of the tops of the three hills in the diagram. And how do I know there are hills? If I look at these the contours, I can see they get higher and higher as they reach a center point. So in the top left, I've got 5 and then 6 and then 7 for my contours. If I want to estimate the coordinates of that highest point, I'll label that the top left hill. The top left hill, my x coordinate, I don't know, maybe about 3, and the y coordinate about 7. It's not a precise thing when we're working on a graph, of course. So there would be one hilltop. Let's go to the lower left, the one that's on the edge of the graph. At the lower left of the graph, that x coordinate looks like it might be 0 if it really is on the edge of the graph. And then the y coordinate would be maybe a little above 2, maybe 2.3, something like that. You could, approximate something a little more, a little less would be fine. And then let's go to the bottom right hill or mountain. And if we look there, it looks like the middle somewhere around that dot. And that coordinate might be, x coordinate might be just a little bit bigger than 7. And it's hard to tell, but maybe a little under 2, or right at 2, somewhere around there. So I might, as an estimate, say 7.2 and then 1.9. That's good. I'm just going to guess, and your answers certainly could be a little bit different. And then we ask which hill is the highest, and that means we're going to look for the highest contour. That's right at the center there. And so the top left hits a 7, the bottom left hits 8, and the bottom right stays at 7. So the highest contour that I see on this graph would be the 8. So that would be the bottom left reaches a height of 8. All right, and just a little more visualization with this. Notice how if we start on the top of any of the hills and start walking in any direction, we start crossing contour lines with lower numbers. And that means we would be going downhill. And if we were to turn around and the numbers start to increase, then we'd be going back uphill. So going from left to right across the graph, I'd be going downhill for a bit, hit a low point, and then start going up again if I'm at sort of the level of those bottom two mountains. So it's just useful for visualization. So here's another contour diagram. We're actually going to try to calculate some partial derivatives with this. So notice, here is another contour diagram down below. First, use it to find two locations, f of 3.1 and f of 5.2. We'll start with f of 3.1, and the number that's going to go in the blank is going to be the contour line that it's on. So x is across the bottom again, y is vertical. So 3, 1 would be located with this intersection, 3, 1. And so the contour line that it is on is labeled with a 1. So that would be my answer. F of 3, 1 is 1, since it lands on a contour line labeled 1. And if we locate f of 5 comma 2, the point f 5, 2, let's see, x is 5, y is 2, would be at this location. And that is on a contour that's labeled with a 3. So f of 5 comma 2 would be 3, since it lands on a contour line labeled 3. So next, think about changing the inputs. If we increase x, we will move to the right on the graph. All right, because across the bottom, 1, 2, 3, 4, 5, 6 moves to the right on the graph. So starting at the point 3 comma 1, if we take one step to the right, we would land on the point 4 comma 1, which is now on a contour line labeled with a 2. So the output of f increased from 1 to 2. All right, so we're talking about change. That's the derivative stuff. If we increase y instead, we would move up the graph because the labels for the y-axis are getting bigger as we move up. Now, starting at the point 3, 1 again, we'd move to the point 3 comma 2. And we're not on a contour line anymore, but we see that the output of f would be something less than 1 because of the pattern of the contour lines. We're somewhere between 0 and 1. So the output of f as we moved up decreased from 1 to something less than 1, maybe 2/3 or something like that. So that gives us an idea of what it means and how things can happen. We can increase when we move in the x direction and decrease in the y direction, or some other combination of changes. So next, we'll see how to notate and find our partial derivatives using formulas. I'll come back and start that in part 2.